Hi everyone. Today we're going to begin talking about differential equations. And just as an introduction, many of the principles in science and engineering concern relationships between changing quantities, such as the rate of growth of a bacteria culture with respect to time, the rate of growth of population, or the rate at which a virus spreads in a given population. And how do we represent rates of change in calculus? Well, whenever we hear the word rate or change, we think of the derivative. So the equation in the do now is an example of a differential equation. How would we define a differential equation? The definition is the following. A differential equation is an equation that contains derivatives. The order of a differential equation is the order of the highest derivative. So the differential equation in the do now has an order of 1. And we will be considering differential equations of the first order and discuss a way of solving them by two different methods. One is graphically, and the graphical representation for the solution of a differential equation is called a slope field. And then we'll talk about the analytical or calculus solution. Okay, so let's go back to the do now and recall, what does this equation mean geometrically? Well, it's very important to remember that the derivative of a function represents the slope of the tangent line to the function at a given point. So if we were to write this differential equation in words, we would say the following. Means the slope of the tangent line to the curve in the xy plane is negative the x-coordinate divided by the y-coordinate. So it's very important to remember that a derivative is the slope of the tangent line to the curve. Okay, this is very, very important. Okay, so what we're going to do is we're going to pick points on the xy plane, find the slopes of the tangent lines to the curve at each of those points, and draw tiny tangent segments. So let's take a look at the next page. This is so hard. Okay, let me just go back. Okay, so here I rewrote the differential equation, dy dx equals negative x over y. And I have a table of points in quadrants 1, quadrant 2, quadrant 3, and quadrant 4. And what we're going to do is we're going to use the formula for this derivative, take the opposite of the x and divide it by y, and apply it to each of these points, each of these ordered pairs. For instance, for 1, 1, we have negative 1 divided by 1, which is negative 1. So we put a negative 1 in there. For 1, 2, we get negative 1 divided by 2, and we get negative 1/2. 1, 3 gives us negative 1/3. In the second quadrant, if we pick negative 1, 1, we have to take the opposite of negative 1 and divide it by 1, which gives us just 1. If we take the opposite of negative 1 and divide it by 2, we get 1/2, and so forth. In the third quadrant, here, when we take the opposite of negative 1 and divide it by negative 1, we're back to negative 1, and negative 1, negative 2 gives us negative 1/2. Negative 1 divided by negative 3 gives us negative 1/3. And in the fourth quadrant, if the x values are positive and the y values are negative, if we have 1, negative 1, we have a negative 1 divided by negative 1, which is 1, a negative 1 divided by negative 2, which is 1/2, etc. So I'd like you to pause the video and fill in the rest of the values in the chart. Okay, let's fill in these values. So for 2, 1, I take the opposite of 2 and divide it by 1. I get negative 2. For 2, 2, the opposite of 2 divided by 2 is negative 1. The opposite of 3 divided by 1 is negative 3. And the opposite of 4 divided by 2 is negative 2. Okay, now in the second quadrant, the opposite of negative 2 divided by 1 is 2. The opposite of negative 2 divided by 2 is 1. The opposite of negative 3 divided by 1 is 3. And the opposite of negative 4 divided by 2 is 2. So we see a little bit of a pattern here. Here we would think that quadrant 1 matches quadrant 3 because we're taking the opposite of a negative x value and dividing by the y value. So we should get negative 2, negative 1, negative 3, and negative 2. And similarly, since the x values are all positive and the y values are negative, when we take the opposite of the x-coordinate and divide it by a negative number, we get a positive number. So we think that this would match quadrant 2, which is 2, 1, 3, and 2. Again, I am just using this formula and substituting the x and y values to get the slope. Okay, now what do we do with those? Well, to draw a slope field, which represents the family of curves that satisfy the differential equation, we proceed as follows. Let's take 1, 1. So we make a point at 1, 1. I'll do this in blue. And we have to draw a tiny tangent segment at that point with a slope of negative 1. Okay, so let's do that. Now remember, slope is rise over run. So we go up or down in the negative direction for down, up for the positive, and then right or left, right positive, left negative. So at 1, 1, the slope is negative 1. So we go down 1 and go, we go up, we were right, down 1 to the right 1. And imagine drawing a tangent connecting these 2 points. Well, we're going to make a tiny tangent segment here. Imagining we're connecting this point to that point. But I will erase now this point. Oops, wrong eraser. I'm going to erase this point here. Okay, so that's our tangent segment. All right, let's try 1, 2. So we go to 1, 2. The slope is negative 1/2. So we go down 1 to the right 2, so we're here. So imagining connecting these points, so we make a tangent segment here, and that would be a tangent segment with a, I just erased it, with a slope of -1/2. So it looked something like that. Okay. Now for -1/3 at 1, 3, we go down 1 to the right 3. We're at this point. So we connect these points and we get a tangent segment this way. Okay. And we proceed in a similar fashion. In quadrant 2, at -1, 1, we make a point there. Oops, 1, 1. We make a point here. And the slope is 1. So we go up 1 to the right 1, connect, and there's our tangent segment. So this is how we make a slope field. I'd like you to fill in the rest. Pause the video and make tangent segments at every point in this table. Okay, I drew the tangent segments for you in the other quadrants, and your slope field should look something like this. Notice that we didn't consider the case when x equals 0. When x equals 0 and y is not equal to 0, our differential equation becomes 0. So to represent tangent segments with a slope of 0, we have horizontal tangent segments. So when x is 0, we're going along the y-axis. So we could draw little horizontal tangent segments. Notice we do not include 0, 0 because that is totally undefined. Now, when x is not equal to 0 and y equals 0, the derivative does not exist. And in this case, we draw vertical tangent segments along the y-axis. Along the x-axis. So we could put vertical tangent segments here. We may see that in a few slope fields in the future so that you're aware of it. All right, but it looks like if we had completed this entirely, that the solution to the differential equation would be a family of circles with a center at the origin. So let's go to the next page and write this out. So the solution to the differential equation dy dx equals -x over y appears to be a family of circles with the center at the origin. And the equation of the family of circles with centers at the origin would be x squared plus y squared is equal to the radius squared. Or in this case, I'm just going to write x squared plus y squared equals a constant. Okay, now let's try to prove this analytically. We'd like to show that we will get a family of circles when we solve this using calculus. So we write the differential equation, and we think of the dy as a differential of y divided by the differential of x. So treating this as a proportion, we can cross multiply and integrate each side with respect to that variable. So this side will give us -x squared over 2 plus some constant I'll call C1. This side will give me y squared over 2 with some other constant C2. However, to make it easier for ourselves so we don't have so many constants, we could bring the C1 and C2 over to any side we want. Let's agree that we will bring the final constant over to the side with x. So I have we'll write down, remember, to make the algebra simple, write plus c on the side with x, because our goal is to isolate the y eventually. So we could just write this as negative x squared over 2 plus some c equals y squared over 2. So from here, we could jump down to here. All right. Now, if we multiply both sides by 2, and bring this x squared over with the y, so we get y squared plus x squared equals 2c. Notice that 2c is some constant, and we do get a family of circles centered at the origin. Okay, so we were talking about the analytical. However, if we wanted one such curve, what additional information do we need to make the circle unique? Well, what we do need to make a unique function, and a circle isn't a function, but we'll talk about that in a minute, is to find the unique solution. Okay, so to find a unique solution, we need a point on the curve. And if we have a point on the curve, we would be able to solve for the constant. Okay, so let's go on to the next page and look at that. So suppose we said, find the equation of the curve that satisfies the differential equation dy dx equals negative x over y and contains the point 1, 2. Okay. Well, we solve this differential equations and we would still get x squared plus y squared equals k. Now we substitute x equals 1 and y equals 2 to find k. So we get 1 squared plus 2 squared equals k, and k is 5. So the circle that we're talking about is x squared plus y squared equals 5, which has a radius of the square root of 5. But a circle is not a function. To make a circle into a function, we either look at the upper semicircle or the lower semicircle. And this is what happens when we solve for y. So if we isolate y here, y is equal to positive or negative the square root of 5 minus x squared. Okay. Y equals positive the square root of 5 minus x squared is the upper semicircle. And y equals negative the square root of 5 minus x squared is the lower semicircle. So there are two possible curves that could satisfy this, but we have to pick the curve that contains the point 1, 2. And our guess would be this one. If we substitute x equals 1 and y equals 2, then we have 2 equals positive the square root of 5 minus 1 squared, which is 2. So for this differential equation containing the point 1, 2, the solution is y equals the square root of 5 minus x squared. But if I change the initial condition to 1, negative 2, you'll see that 1, negative 2 fits into this curve. Negative 2 is equal to the opposite of 5 minus 1 squared. That works. So that curve would be the lower semicircle, the negation of the square root of 5 minus x squared. Let's see what this looks like on the calculator. Okay, let's take a look at another example. Find the curve in the xy plane that passes through the point 0, 3 and whose tangent line at a point xy has a slope of 2x over y squared. So in this problem, we have to realize that if the slope is 2x over y squared, we should be able to write this differential equation, dy dx equals 2x over y squared. And we want the curve that contains the point 0, 3, satisfying that differential equation. So we cross multiply again, integrate each side with respect to that variable. Here we get y cubed over 3. We're going to save the c on the x side, and the integral of 2x is x squared. Now, at this point, we use the initial condition and substitute x equals 0 and y equals 3 to find the c. It's good to find the constant immediately after the calculus, after the integration. Algebraically, it's easier. So we have 3 cubed over 3 equals 0 squared plus c. c is equal to 9. So our family of curve, well, the curve is y cubed over 3 equals x squared plus 9. But it did say to find the curve. And to find the curve, we have to make sure that we have only one possible curve. So we'll have to isolate y. So if we multiply everything by 3, we get y cubed equals 3x squared plus 27, and take the cubed root. And the cubed root doesn't introduce a positive or negative, so we're safe. So this is the curve that satisfies the differential equation with the initial value of x equals 0 and y equals 3. Let's take a look at an AP question. Okay, now this AP question was from 1988, BC4. And it says that let f be a function with f of 1 equals 4, such that for all points xy on the graph of f, the slope is given by three x squared plus 1 divided by 2y. Okay, now the first one says, part A says, find the slope of the graph at the point where x equals 1. Well, f of 1 equals 4 means that when x is 1, y is 4. So to get the slope of the graph there, we simply substitute into the differential equation dy dx equals 3x squared plus 1 over 2y. So dy dx, when x equals 1 and y equals 4, is just 3 times 1 squared plus 1 over 2 times 4. And that gives us 3 plus 1, which is 4 over 8, and the answer is 1/2. So I hope that that is correct. Okay, that was an easy question. All right, part B says, write an equation for the line tangent to the graph of f at x equals 1. and use it to approximate f at 1.2. Okay, so we know that 1, 4 is the point of tangency. We know that the derivative is a half. So putting it in point slope form, we get y minus 4 equals 1/2 times x minus 1. And that is the equation of the tangent line at that point. Now, if we want to use the tangent line to approximate the function at 1.2, we'll add 4 on each side. And the function f is approximately equal to the y value on the tangent line at that point. So f at 1.2 is approximately equal to 1/2 times 1.2 minus 1 plus 4. So that's 1/2 times 0.2 plus 4. So let's see what we get. Well, this is 1/2 times 2 times 2/10 or 1/5 plus 4. So the answer is 4 1/10 or 4.1. And that would be our approximation. Now, part C says, find f of x by solving the equation dy dx equals 3x squared plus 1 over 2y with the initial condition f of 1 is 4. Okay, so first we have to solve this analytically. We write our differential equation. We cross multiply. And we integrate each side with respect to that variable. And remember, the plus c goes on the x side. So the integral of 2y is y squared. The integral of 3x squared is 3x cubed over 3 plus x. So this can be written as y squared equals x cubed plus x plus c. Now, once we integrate, we use our initial condition that when x is 1, y is 4. So we get 4 squared equals 1 cubed plus 1 plus c. That's 16 equals 1 plus 1 plus c. 16 equals 2 plus c, so c is 14. So it looks like our curve, well, we have this as our solution. Y squared equals x cubed plus x plus 14. But it did say to find f of x, a curve, 1y equals. So we isolate y here by taking the positive or negative square root. And there are two possible curves. So we have to check on which curve is our initial condition in. Is it the positive square root of x cubed plus x plus 14? Or is it the negative square root of x cubed plus x plus 14? Well, let's try for x equals 1. 1 cubed plus 1 plus 14. That gives us a square root of 16, which is equal to 4. And that is the y value. So our solution is this. If we substitute x equals 1 here, the difference is that this side is still root 16, but the negative symbol in front of the radical makes the y negative 4. So this would have been the solution if we had f of 1 equals negative 4. So our correct solution is this. And it did say to use this function to approximate f of 1.2. Oh, that was part D. Let's look at part D. I'll write it up for you. X cubed plus x plus 14. So part D says, use your solution in C, part C, to find f of 1.2. So our solution was y equals the square root of and now this is our f of x. And if we substitute 1.2 in here, well, we have to square 1.2, so this would give us 1.44, and when we multiply that by 1.2, 8, 8, 2, 4, 4, 1, 8, 12, 7, and 1. Okay, so I believe we get, now let me just make sure I did this correctly. 8, 8, 2, 4, 4, 1, 8, 12, 7, and 1. Yeah, so we get the square root of 1.728, and 1.2 plus 14 gives us 15.2, and 1.728 plus 15.2 gives us 16.928. And this piece, I'm sure, was on the calculator part. So if we use our calculator to find the answer, we get, with the calculator, we get 4.114. And remember, the rule is 3 places after the decimal point. And that's the value of the function at 1.2 because we found the function. Whereas in part B, the tangent line approximation was 4.1, which is pretty close to the actual value on the curve. So that tangent line approximation was very good. Okay, so I'd like to summarize how to solve a differential equation. And these differential equations are called separable differential equations because we could bring the x's and the y's all on one side. So to solve a separable differentiable equation, the first thing we have to do is cross multiply. And bring all the x terms with dx and all the y terms with the dy. Never divide by a dx or dy. Leave the dx and dy where they fall in the cross multiplication. Just divide the expressions with x's or y's. 2. Integrate both sides with respect to the variable and remember, add the plus c on the side containing the independent variable x, or it may be t if it's in terms of time. 3, use the initial condition or or the given point, to find C. Okay. And next, solve for y if there are two solutions, and pick the curve containing the given point or the initial condition. Okay, it is very important that we solve a differential equation in this way. Once we integrate and have the plus c, we immediately find the value of that c and then proceed to isolate the y. So hopefully that would be helpful. We will look at more differential equations later on. Okay, so I'd like to show you how to graph a differential equation on our TI CAS. So we hit menu, and on menu we're going to put add graphs, and we go to menu again, and notice the third option that says graph entry edit. We click on that, and notice at the very last choice we have differential equations. So we could plot various different equations here, but we're going to use the differential equation mode. So we click on that, and notice that my window changes completely. This means the first function, y1, and there's a derivative symbol right here. So we're going to type in our function, the differential equation, negative x divided by, but instead of y, we have to, whenever there's a y in our differential equation, it must match the y here. So we have negative x divided by y1. Okay, now when we press enter, hopefully we'll see the slope field. And there it goes. This is what we had on our grid that we did by hand. And we see that we still have a family of circles centered at the origin. To look at a particular solution to the differential equation, we need a point. So, okay, let's go back up. Okay, so that's the x sub 0, y1 sub 0. That's the initial point. So we're going to put it here. We're going to type in 1, 2. And that's our initial condition. Notice it's over here. Okay. And here, this calculator, I don't know why it's giving us these areas, but this is the semicircle right here that satisfies the differential equation with that initial point, which we discussed before. Okay, so that's our demonstration.